Hi, so I'm gonna do number 6, least squares most fun. And for this question, we're gonna skip, or for this walkthrough, we're gonna skip part A, because this part was already covered in lecture 14. So if you want a more detailed description of how to get the solution for part A, I would recommend looking at lecture 14. But for part B, show that when x is full rank and squared, data NP is equal to data LLs. In other words, show that this inequality holds. So let's do that. For this question, you need to know some linear algebra, be sharp on your linear algebra, and dealing with inverses. So what we could do is first, we could multiply both sides by x on the right side. And what this does is it cancels these two terms out, because this is the inverse, right? So then it becomes xt, xxt, x is equal to I. And then what we could also do is times x on the left side. So x, or I is the standard matrix where it's 1, 0, 0, 0, 0, 0, 0, 1 diagonal, right? 0, just so you know. And when we multiply x on the left side on both sides, we get that these two terms are the same. And this is the inverse. So it cancels out and makes an I. The I matrix. So Ix is equal to Xi. And this is just itself, x itself, so it's x is equal to x. So that's how we show that this equality holds. Now for part C, what we want to show is that this holds true when we're using this type of data. So what we do know is that this error, this thing, is equal to y equals y hat, which equals 0. I mean, not y equals to y hat. Y minus y hat equals 0. And then what we do know is that y hat, or what we should know is that y hat is equal to x theta. And in this case, theta would be theta NP, so that's what our optimal solution would be. So we do E equal y minus x theta NP equals 0, which equals y minus x, and you just plug it in, xt, xt, inverse y. And then we would have that this is inverse of this, which cancels out. So we have E is equal to y minus iy, which is equal to y minus y, which is equal to 0. So because this summation is equal to this, and we found out that it's also equal to 0, we prove that this summation is equal to 0. Yeah.